All right, so this is pretty much the title here is Ballistic Pendulum. Okay, so let me start with two things that this lab pretty much, two concepts it covers. It covers momentum and energy. So we already talked about energy in, let's say, lab six. Sorry, yeah, lab six and lab five even. Both of those were, energy labs. So I will briefly then, cover energy concept that is related to this lab specifically. Again, I'm not going to go back and give you the theory of the energy. At this point, you should already know that. But I'm going to, talk about what the momentum basically represents and under which condition momentum is conserved. So generally what we talk about here, momentum, which is the, P here is for momentum, right? It's a product of the mass and the velocity of the object. And it's a vector always in the same direction as the velocity. So for example, if you have an object, that has a mass of, let's say, a 1 kilogram, moving with the velocity of, I don't know, let's say 3 meters per second, let's say I hat, then momentum will be 1 kilogram mass times 3 meters per second I hat for the velocity. So that's 3 kilograms meter per second I hat. That means here's the momentum magnitude, right? And this is the direction. That means the momentum in a way always has the same direction as the velocity at that instant. All right, so technically then you can say, right, object has no momentum if it's at rest, and it has a momentum if it's moving. Now, what more important as a sort of like a physical concept is not just necessarily momentum, but change in momentum. So let's say delta P, which is final momentum minus initial momentum. Okay. So let me do this. Our book, and I like that notation that our book is using, is generally uses prime for the final momentum. So let's say I'm going to put like P prime, that's the final, minus P, that's the initial. So prime is the final momentum, P is the initial momentum without any prime. That means this is M times V prime minus M times V. So again, this is the final momentum and this is the initial momentum. So the idea here is this. So for example, you have an object that has mass M, and let's say this object is at rest, which means that V here is equals to 0. And obviously that, that's the initial velocity I'm talking about. So another important thing here is, what do we need in order to change the momentum of the object? Now, if you think about it, right, let's say if you have an object just sitting there, like a box, just sitting there with initial momentum to be 0, right, with initial momentum of 0 because it's not moving, in order for us to change momentum, and momentum changing at this point is like any direction motion, right? So it could be to the right, to the left, up or down, as long as it starts moving. Because if it starts moving, there is a velocity and there is momentum. Now, in order for us then to change momentum, that means we have P prime that is not, let's say, 0. Obviously, you can see, right? One thing we can do here is we can apply force. So then let's say if you apply force, push the box to the right or to the left, right? But some kind of force that you apply, then it's going to start moving. And then one thing we can say is then there's a change in momentum as long as there's some kind of applied force, and this applied force acting doing some short period of time. So that's why changing momentum then is equals to then the integral of F dt from T1 to T2. So this is generally then the equation for the change in momentum. There has to be a force acting on it during some very short period of time. And this dt generally is the time during the contact. That means there has to be a force acting on it that changes the momentum, okay? Um, and this dt represent that period where the force is applied and the change in momentum is happening. So generally that's a very short time, and that time is again assumes that during that time there is a force acting on it. That force can be a constant force. That force can also be a variable force. So this, the integral on the right side of the equation is also known as the impulse force sometimes. So J is for the impulse. So we call it impulse force. So technically J is not a force. So when we call it impulse force, we're basically saying there's a force acting on an object during some short period of time. So that's why you can see, right? J is the, in a way, integral of F dt rather than just F. All right, so that means, they have a delta P, which is equal to impulse. You can say then there's an impulse force acting on the object, then there's a change in momentum, where J itself is then the integral of, F dt, okay, going from T1 to T2. Okay. Any questions? All right. Now, if you have one object like this, this box over here, then technically any type of force acting on it during some short period of time has in a way ability to change its momentum. Okay, so for example, you push it to the right, you push it to the left, you're going to change its momentum. You have you're dropping an object, you have let's say a tennis ball, you drop it, it goes down, then it hits the ground, and there's a normal force from the ground, and then it's going to bounce back, and there's a change in momentum, right? Because it's going down, that's a downward momentum. Then after that, it's going up, so upward momentum. So there's a change in momentum. And then let's say what happens, what made the object change momentum? Well, during the contact with the surface, let's say there's a normal force, and that normal force makes the object, so there's a downward momentum, and then there's now upward momentum, right? There's a changing momentum. And the T represents the, during the collision, the time. Now, one thing then we can do here is this. We can have a system of particles. And I'm going to, this object, I'm going to refer to as a particle. So, because in a way, its size is still not important for us. So we have a system of particles. Could be 2, 3, 4, you name it. But I'm going to look at it in terms of system of, let's say, 2 particles. Now, my system going to have 2 objects moving toward each other. So this is going to be M1, this is going to be then M2, this is going to be V1, this is going to be V2. Okay. That means what I have here is I have P1 is the momentum of object 1, which will be M1 times V1. P2 is then the momentum of object 2, M2 times V2. So because it's a system, I'm going to take them together to be part of my system. That means now what I have here, I have a momentum total, which is then P1 plus P2. That means momentum of object 1 plus momentum of object 2. And what I have here, you can see, right, those 2 particles moving toward each other. Well, eventually they're going to collide, right, if they continue moving toward each other. So what I am, presenting here is my system basically before the collision. This is before the collision. So that means, in a way, this is then the total momentum of the system before the collision, which will be then M1 V1 plus M2 V2. Then obviously they're going to collide. So when they collide, so let's say here's object 1, here's object 2, okay, object 1, object 2, they're going to collide. So this is, you can say, like, let's say this is during collision. And one thing I'm going to say is that those objects are on a, let's say, frictionless surface. Okay, they're on a frictionless surface moving toward each other, and then they collide. Okay. And now when they collide, they exert force on one another. So there's a force that 2 exerts on 1, and there's a force that 1 exerts on 2. Okay, basically action reaction forces, which then make individual particle to change their momentum, because if there's a force during the contact, right, their momentum will be changed. But then what I have here is I still have, a system. So then what I'm going to look at here is the after the collision, which means then I have M1 moving, let's say, to the right after the collision, right, bounces back. So this is this is M2. So V2 prime, and here's M1. Now it's moving to the left. This is then V1 prime. That means, they're moving towards each other, they collide, then bounce back. So then this is then my system after the collision. That means I'm breaking it down into 3 different parts: before collision, during the collision, then after the collision. Okay. And then what I can see here is this. This is then my total momentum after collision. I'm going to put prime, which means this is then M1 V1 prime plus M2 V2 prime, where V1 prime is the speed of velocity of the object 1 after the collision. V2 prime is the velocity of particle 2 after the collision. Okay, so this is P total prime, which is the system momentum after the collision. Now, one thing I have done here is this. If I'm looking at sort of like, let's say, change in momentum, delta P, then delta P here is equals to P total prime minus P total, which is system momentum before, after minus system momentum before. And we know then delta P here is equals to, let's say, integral of F dt, but generally if there are more than one force, it's net force dt from T1 to T2. Now let's look at then what is my net force. My net force here is F12 plus F21, which is the forces acting in the system during the collision. Now, what we have here is for those two forces are actually forces inside my system. So they are known as internal forces. And internal forces, F12 and F21, because they are also action-reaction forces, we know that F12 and F21 have the same magnitude, opposite direction. So then technically, F21 is equal to negative F12. So I can say F12 plus, well, F21 is negative F12, so I can say negative F12, and what I will see here is my net force equals 0. Again, because those forces are internal forces, and let's say at this point I have 2, but I can have more than 2. I can have, like, let's say 4, 6, 8, and it has to be multiple, right? Because there are always action-reaction. For every force, there is an equal but opposite force. And all the internal forces will always sum up to 0. That means when I'm looking at this change in momentum, which is P total prime minus P total, the right side of the equation now is then going to be 0, because there are no net force acting on it. And if there are no net force or no external forces acting on it, or all the forces are internal, then what I can have here is this. That means there's no change in momentum, which means momentum total prime equals momentum total unprime. That means momentum before and after of the system is exactly the same. And this is what we have for the conservation of linear momentum. That means system momentum is conserved before and after collision. That means I can go back and, in a way, completely ignore this portion of my, let's say, the 3-part, where I have before and after, and during the collision I can completely ignore, because during the collision nothing really happening that I can use, because I have forces acting on the system that they cancel each other. That means all I have that are useful for me is before and after, and the sum of the momentum before and after is constant, conserved. That means, in a way, for all the conservation of momentum problems, whenever you have 2 particles, you can basically write it like this: M1 V1 plus M2 V2 equals M1 V1 prime plus M2 V2 prime. So that's the equation for the conservation of momentum for 2-particle system. All right, so then from here, we can look at collisions because there are two types of collisions. There is elastic and there's inelastic. So two types of collisions, elastic, inelastic. And there are some similarities between those collisions. And the similarity is that momentum is conserved. That means P total prime is equals to P total for both of those. That means this equation applied to both type of collisions. Momentum is conserved regardless if it's elastic and inelastic. Now, the difference between them is then in terms of the energy of the system. Because when you look at the energy of the system, energy prime is equals to energy, that means energy after is equals to energy before for the elastic collisions. That means energy is conserved as well. That means in a way you have two conditions. Momentum is conserved and energy is conserved. For the inelastic, momentum is conserved, but the energy not conserved. And that's the big difference. That's why there are two types of collisions. One in which momentum and energy is conserved, the other one where momentum is conserved but energy is not. And what we have here is elastic and inelastic collisions allow us to basically have, more realistic and a little more theoretical type of collisions, because any type of real life collision is basically inelastic. And maybe when you go and talk about at the particle level, subatomic particles and things like that, then you might see some elastic collisions. But generally, then you can say that more or less most collisions are inelastic. Now, how do we know again if the collision is elastic or inelastic? Well, the only way for us to know is to calculate the energy before and after. If the energy is the same before and after, it's an elastic collision. If energy is not the same before and after, then it's an inelastic collision. Then you can calculate how much energy was lost and things like that. Because if it's an inelastic collision, you always lose energy. That means after the collision, energy of the system is always less than before, because a lot of the energy will go into heating the surface of objects and things like that. All right. So any questions, by the way? So then here's what we have. For our lab, the type of collision that we are going to be looking at is the inelastic collision. That means we have M1V1 plus M2V2 equals, that means you have two objects basically before the collision. So let's say here's the two objects before the collision. So you have then M1, here's you have M2. Now, let's say M1 is moving with some velocity 1, and M2, for example, moving with velocity 2. Inelastic collision means that after the collision, there will be energy loss. So a lot of times collisions, when there's a collision, you're not going to really be able to tell if it is elastic or inelastic unless you calculate the energy before and after. But there are specific type of collisions, inelastic collisions, where object would, after the collision, stick together and move as one. So let's say this is before the collision, and let's say after the collision, let's say they stick together, I don't know, and let's say move with one final velocity. All right, so who knows the name of this type of collision? What is this type of collision?
Perfectly inelastic.
Perfectly inelastic, yes. So perfectly inelastic is very specific type of inelastic collision where the system has two objects stick together after the collision. Not every inelastic collision objects stick together, But every time where objects stick together, it's definitely an inelastic collision. So that's why it's a special case of perfectly inelastic. So perfectly inelastic. That means after the collision, what I have one object with combined mass and then times v prime. Okay. So that means this is the equation of a perfectly inelastic collision where objects stick together. Okay. That means there's only one final velocity and they're both going to be moving at that same final velocity. A lot of times I can make this problem a little bit simpler. For example, if I make the object 2, for example, at rest, so this is equals to 0, then what it does is just basically it eliminates this as well. Okay, then I have, even a little bit simpler, m1 v1 equals m2 plus m1 plus m2 times v prime. And technically, this is the equation we're going to be using for our experiment. That means we have two objects that gonna, collide, where object 2 initially at rest. Then after the collision, they're gonna stick together and move as one with some final velocity. Okay. Now let me give you the experimental setup for our experiment. So because it's a little bit different, because we do have a pendulum. If you remember, it's ballistic pendulum, right? The name. So here's then our object 1, and our object 1 going to be a bullet. So M1. Okay. So or if you want, I can just put like MB for a bullet. Let's say now this guy here is moving with some velocity. So this is going to be VB. This is the initial velocity of the bullet then. And then we have a pendulum. And the pendulum is basically going to be an object 2 like this, but object 2 is actually connected to some pivot point. So it is, let me put MP for the, pendulum mass, and it is going to be at rest. VP equals 0. So it is going to be rest. So this is my system before collision. Okay. Now, after the collision, what happens here is bullet gonna embed itself into the, pendulum, right? They're gonna stick together and they're gonna move. But what happens here is, let's say, so like, let's say when after the collision, this is gonna, so let's say it's gonna stick to the pendulum and they're gonna be moving with some V prime. V prime is the final velocity of the system. In a way, this is my, what's gonna happen, let's say after. Okay, like I'm talking about like right after the collision. Okay. So if I'm writing down the equation of my system, let's say, of the experiment, so I have then m1 v1, remember, plus m2 v2 equals m1 plus m2 v prime. That's basically the general equation. Then one thing I'm going to say here is this. So it's my object 1 is the bullet, so m bullet times v bullet, plus my object 2 is the pendulum, and it has no initial velocity, so it's 0. It has no initial momentum. And then this is equals to mass of the pendulum plus mass of the bullet, then times v prime. That means it's mbvb equals mp plus mbv prime. Now, our goal for this experiment will be this. We want to find this guy over there. What is the velocity of the bullet before the collision? Which mathematically is just mb plus mp divided by mass of the bullet, then times v prime. That means this is our equation to calculate the velocity of the bullet. But the only thing here is this. You're going to be given the mass of object 1, mass of object 2. That means you have mass of the bullet and mass of the pendulum. But if you have this equation to solve for the velocity of the bullet before the collision, you're also going to need this velocity of the system after the collision. And that's not something you're given directly. So that means, in a way, from what you have, you're not going to be able to calculate the velocity of the bullet. But luckily for us, because of the type of experimental setup that we have, the system after the collision, let me kind of do it like this. So the system after the collision gonna do this. So think like this. After this is right after the collision, and what will happen here is this. So taking this to be right after the collision, where now they both of them together, moving with some, let's say both of them together moving with some velocity, right? This like let's say sort of like a v prime. Because then the pendulum is fixed at this point, it will allow the pendulum and the bullet, instead of moving to the right, it's going to allow them move some angle theta with respect to this vertical line, right? So it's going to move like this, but then eventually it's going to slow down and stop until it reaches, some height. It's going to stop and then come back down. Okay. That means for my experiment, as soon as, let's say this is the pendulum, bullet hits, they're going to go up, stop, and then come back down. So that means right after the collision and maybe a few seconds after the collision, I have a experiment like this. And what I can do here is I can use then conservation of energy to find this v prime, because v prime is the velocity of the system after the collision. But for the this particular let's say what happens after the collision, right, when the bullet and the pendulum start moving upwards, then stop and come back down, that becomes basically energy type of problem. Because what I have here is I have an object that at the bottom, and then it goes up and stops. So basically it has some kinetic energy. Then it conserves its kinetic energy. It conserves its energy by converting kinetic energy into potential energy. That means what I can do here is this. I can take this to be my reference vertical position, and I can say that this is my, so let's say this is point 1 and this is point 2. Then object goes from point 1 and point 2, and the only force technically making it move is the gravity, because the gravity is the one going to convert kinetic energy into potential energy. Then in a way what I can say is this: kinetic energy at point 1 plus gravitational potential energy at point 1, then it equals to kinetic energy at point 2 plus gravitational potential energy at point 2. But because my system going to stop at point 2, let's say here I have v double prime, but v double prime is going to be 0, then I can say that there is no kinetic energy at point 2. It's going to stop before coming back down. Since point 1 is going to be my reference position, there's also no potential energy there. So then my conservation of energy is just any kinetic energy that I had at point 1 will be then converted to the gravitational potential energy at point 2, which means then 1/2 m1 plus m2 times v prime square equals then m1 plus m2, where again m1 and m2 is the my object masses, right? Then times g, then times vertical position of 2. And again, I don't even care about their mass at this point for this particular part. And what I have here is then I have 1/2 v prime square equals gy2, or v prime is equals to square root of 2 gy2. That means I can calculate my final velocity after the collision by just looking at how high the system will go a few seconds after the collision before it stops and come back down. All I need to get here is measure basically that. And that's what we have. Because once you have that, then you can come back, bring that into this equation, and solve for the VB, velocity of the bullet. That means this is equals to m bullet plus m pendulum divided by m bullet, then 2gy2. Okay. Or if you want, you can say that just 2gh. Okay. And that's basically the equation that we're going to be needing to solve for the velocity of the bullet before collision. Right. Any questions?
Professor, I have a quick question.
Yes,
What exactly is v double velocity double prime again? That's just the velocity is zero at the height of the pendulum swing.
exactly.
Okay.
Because it is it is connected to this pivot point. So then it's gonna go up, but when it's going up, the gravity acting against it, so it's gonna slow down until it stops, and then comes back down. Right? Think of like a pendulum, right? Pendulum when it swings up, it's gonna slow down, stop, and come back down, right? So the just basically the same idea.
And so that's how we're able to cancel kinetic K2 because it should be zero because there's only potential energy at that point when it's at the height, right?
Exactly, because one of the the beautiful part about energy approach is that you don't care how you get to point two. All you want to know here is the energy at point two. What type of energy you have at point two? At point two, I have only potential energy. Why? Because it's not moving at point two, right? It stops at that instant when it gets to point two, so there is no kinetic energy. That means I can easily get rid of that. And because point one is my reference position, I get rid of that as well. That means my energy at point one is purely kinetic, energy at point two is then purely potential. And that's why I have conservation of energy where all the kinetic energy of the system, basically, right, after the collision, then is converted into gravitational potential energy. And energy at 1.1 and point two is exactly the same. So I can use that to find the speed at the bottom.
Okay, thank you. And then my last question was we add their masses because we treat it as one object, right?
Yes, because see, for this particular example that I'm looking at, right, this is after the collision, right? When the pendulum and the bullet swings upward. Remember, that's after the collision. That means you already have perfectly inelastic collision, happened, like a fraction of a second before that, and they are moving together as one. So that's why my mass is the combined mass, which I end up not even using because it ends up canceling, from both sides.
Thank you.
All right. Okay, so then let me show you the experiment itself and show you, let's say, what type of measurement you need to make. All right, so here's the, oh, not that. Give me a second. That was the wrong class. All right. All right, there you go. So ballistic pendulum. Okay, again, remember we are applying conservation of momentum with conservation of energy to predict the velocity of a, instead of bullet, we're gonna basically use a marble. Okay. So the experiment is kind of very similar. So think like this. So here we have a, let's say a gun. I think it's right here. Here is the gun. So we're gonna have like a bullet. We're gonna shoot the bullet from here, and this is our pendulum then. Okay. So generally it's kind of fast. You're not really gonna be able to see the bullet moving and then colliding and things like that. But you should be able to do some nice measurements. So let's say, let me clear this and make it a little bit bigger. Okay. So here's then the experiment. All right, there you go. So it's very fast, and in general, it is very fast. Even whenever you're doing experiment in class. But the good thing about here, we can go back and review everything from the scratch. Okay, so thing like this. So what happens here is this. So you can see that, I don't know if you guys will be able to see the bullet. As you can see, right, it's kind of hard to see, but you can see it hits the, let's say pendulum, right? So it hits the pendulum. So for this particular video, what we're gonna do here is we're already gonna look at collision and then what happens after the collision. And you can see right after the collision, the pendulum goes up, reaches some height, and then comes back down. Okay. That means we need to, by the way, here's that marble. So if you kind of look at carefully right there, that small dot, right? That's a marble. And it's not there if you go back a little bit. Let's say, if I kind of go back, there you go. See, it's not there right now. And then you hit it with the marble and then it goes up. So what we do here is this. So we take, there are a number of things we can do. For example, um, the idea here is if I kind of take this, or maybe like, let's say a protractor, and you put it here, so then what your vertical axis is. So let's say like that. And you can kind of put it like this here as well. And then once you play the video, let's say after the collision, you can see it goes up. Now there are two things we can do. Okay. We can see then it kind of reaches this position and stops. You can see there is this X on the pendulum itself. Okay. So what you want to do here is this. So measure how high that X goes, basically that circle with the X, relative to the ground, for example. And then you should be able to find its height. So let's say that's right. What I do here is I'm using this ruler here, right? As like let's say a reference, horizontal line. And then I'm going to show you basically two ways to do that. And then once you have the pendulum, it goes up. Let's say, I think that's probably the highest also. Then you take the next ruler and then measure how high it goes relative to that, first ruler. Okay. And find basically the Y2, right, height. Okay. Remember, the idea here is what we want is this kinetic energy at point 1, because this is now my point 2, is equals to the potential energy gravitational point 2. Okay. So if this is then your horizontal axis, right, and this was like, let's say point 1, you just want to know what is this height. Okay. That's one way to do that in terms of just directly measure this height. Another way to do this would be this. Measure this length of the pendulum. So basically measure this length. This is L for length. That means, and this is also the length of the pendulum. And then this height will basically can be calculated by looking at the total length. That means this length here, and also projection of the length when it's at position 2, which is this one here, which we can see that it's then, it creates a triangle where this is the theta and this is then the, adjacent. That means it's just L cosine of theta. And then L minus L cosine of theta, because this is L and this is L cosine theta. So their difference will give you this, is give you then your height H. Okay. So that's another thing you can do. So that means measuring H You can find the L, you can find L cosine theta, and then find the difference. Or just directly measure that, zero point 0.2 relative to 0.1. Both, versions work. But once you find that, then you need to, once you find the, the height, then you can calculate if you want V prime, which was square root of 2gh, right? And then once you have V prime, go and calculate the bullet. That means what is the speed of the bullet when it's, launched from a gun, let's say. Because from here to there, right, is moving at constant speed, then it collides with the pendulum and makes it, go up some height h. All right. That means for this particular part, that's what you have to do. Okay. So let me clear this. Are you guys okay? Any question in terms of what needs to be done? Okay. So then you can see, right? So here, what you need to do is basically do the measurements, do all your work on a piece of paper, and upload it here. Because I give you the mass of the marble, I give you the mass of the pendulum, okay, and then I give you the length of the pendulum from the upper pivot point. So everything that you need to be able to calculate the initial velocity of the bullet or the marble. Okay. After that, once you calculate that, once you upload your picture and everything, right? So let's say you do the work on a piece of paper, then you upload it here. Then you're gonna like your answer and you're gonna continue. Because so second part is another way of calculating the velocity of the bullet. Okay. So we're gonna calculate the velocity of the bullet, initial velocity of the bullet, by looking at the bullet when it's launched. So as I mentioned, right? So as soon as you launch the bullet, going from, let's say, this point 1 to point 2, which is where the marble is, where the pendulum here is, this distance that the marble gonna cover before colliding with the pendulum, let's call this delta x. During that entire time, that marble actually gonna be moving more or less at constant speed. Okay. That means one thing we can do here is this. See, this particular experiment allows me to really slow it down. Okay, really slow it down. And measure the time it takes for the marble to go, let's say, from point 1 to point 2, something like that, right? That means, you just choose a distance, right, from 0 to 70 or something like that. And then, for example, time it. So let's say, see, this is slow enough that you can see what happens there. There you go. Again, one more time. Oh, I guess I was a little bit wrong. It starts from here. There you go. It starts from here. But again, one thing you have here is you have the distance. You have a ruler that you can use to measure the distance. And then, for example, you can go and look at the instant they shoot the bullet. What you should be able to now see, you can see the bullet, right? Or the marble, if you want to call it. See, now you can go and put it here at, let's say, 0. Or let's say for something like this, even, then you put the 0 here, you reset your timer. And then, for example, you want to measure how long it takes for it to go to a 50 centimeter, let's say. And then once you start, then it basically, syncs the timer with that. So then you can go back. So the 0 was here. And then how long did it take for it to reach 50 centimeters? Then that's basically, let's say, the time. Take that distance, divide by that time, you have then speed. Because as I said, right, the the marble moves at the uniform motion. That means distance over time will give you the speed. And you take the speed and compare it to the speed at doing the for the experiment one. That means this is going to be your uh, speed one, speed two, or velocity one, velocity two, and you want to compare them. You want to compare to see if you are getting anywhere close, same value or not. Questions on this second part? Right, should be relatively straightforward. Next, we have then the last part. So now, if you get a large percent difference, there could be an explanation why. And that explanation can be based on your last experiment. So you like this answer and go to the next one. This one shows a very interesting experiment. You still have the same gun, same pendulum, but when you shoot the gun, there is no marble there. That means you're just basically shooting just blank, just basically just pushing some air. But interestingly enough, here's what happens. Okay, so let's look at it with slow motion. All right. See what happens with the pendulum. Pendulum was actually pushed even though there was no marble. So what do you guys think? What actually was responsible for pushing the pendulum? What do you mean by both? I'm not sure what you mean by that. So let's say what pushes pendulum right now? What, remember, pendulum was pushed in the first part because it collided with the bullet or the marble. So what's the response? There is no marble right now, but it is being displaced, right? It is being pushed. So what's responsible for pushing it?
I was gonna say like the particles in the air, because there is molecules of oxygen and nitrogen in the air. Maybe it's those atoms are being pushed so fast that collectively they're able to move the pendulum.
Exactly. Excellent. Yes, because what you have here is, even though there is no marble, basically you're shooting air, right? And those air molecules actually collide with the pendulum, and it's moving. So that means when you go back to the first part and find the velocity of that perfectly inelastic collision, in a way, what you calculated as an initial velocity was not necessarily the initial velocity of the marble, but initial velocity of the marble plus air combination. So that's why for the second part, in this experiment, when we're calculating the velocity of the bullet of the marble, there is no, let's say, air. We're just looking at how the marble is moving in like, let's say, space, right? We're calculating the distance and time and just finding the velocity. Where using this collision, so let's say during the collision, actually there is a 3-object system. It's the bullet, air, and the pendulum. That's why there's going to be a little bit of discrepancy for the speed of the marble for part 1 and speed of the marble for part 2, because there's also air molecules also involved. All right, so that's basically in a way I kind of gave away the answer for that. All right, any question about this lab? So that's why, as I said, right, this is a really nice lab that allows you to kind of see and work with, a momentum and conservation of energy and things like that. So I think it's a really nice combination of, several concepts put together and give you like a good visual view of everything.
Professor, I have a question.
Go ahead.
How can we minimize error? Because it kind of seems to me like it's pretty easy to get a large margin of error because it's moving so fast. It's almost hard to measure.
Well, that's why, for example, for the second part, you can slow it down in a way. It's basically you have higher frame rate, and it allows you to slow down and be able to see marble moving, and you just easily can measure the distance, time, and calculate the velocity. For part two, even for part one, even though it's fast, well, you don't really need to see any of that. All you need to do here is just measure position of the pendulum before collision, and like right after the collision, and how high it goes after the collision. Let's say when it goes up, swings up and stops and comes back down. So those for those measurements, doesn't matter if it's really that fast. You can still be able to do those measurements. Okay. The idea here is that to understand that um, when you're calculating the velocity of the marble using those two different methods, you will get different values only because you need to also take air into account, which you don't in part one.